Well, thank you very much, everybody. It's a pleasure to be in St. Petersburg. It's a lovely, lovely city, and I'm delighted to be here. What I want to talk about is some work that I started doing for ICANN a few years ago on the DNS name collision problem that was spoken about then in the context of new top-level domains. So as you might remember, recently ICANN created about 1,000 new top-level domains, all sorts of names like .shell, .amazon, .africa, and all the rest of that kind of stuff. But shortly before they were about to announce this program to create all these top-level domains, someone said, wait a minute, maybe these names are already being used on the internet just now. How do we know? Is this a problem? And if so, what can we do about it? So ICANN commissioned a study, and the firm I was working with got the contract to do this initial piece of work. Now, the timing for this was also very, very awkward because essentially we had 6 weeks to do the job. So ICANN wanted the report to be discussed at their meeting in Durban, which was just over 6 weeks away from issuing the contract. And we knew we were going to have trouble because no matter what results we produced, people were going to complain. They would be unhappy because either their favourite top-level domain was going to be blocked because it was too popular, or someone might not find any details at all, and then the whole GTLD program would then proceed. And people would be unhappy about that because many people did not want these new top-level domains to be created at all. They didn't see the need for it or the justification for it. So we expected the results were going to get challenged by everybody. Nobody was going to be happy with what we did. But then when we actually started to look at the resourcing of this thing, the 6 weeks limit became a real concern. So what we had to try to do for the DNS component of the study was find out how often these new top-level domain strings have already appeared in the root server traffic. Are they localized? Are they all coming from one place? Or are they spread from all over the internet? Are they coming from resolving servers, or are they coming from stub resolvers? And how does this compare with traffic for the existing top-level domains? That was kind of where we were trying to figure this whole thing out. So the first thing we had to do was find out how we're going to get access to the data. And the thing we did there was we were quite fortunate that there was a Reid meeting taking place in Dublin, and most of the root server operators were physically present in Dublin for that meeting. So we could have good discussions with the root server operators about what data they had, what kind of assistance they could provide, what kind of support was available, and so on. It turned out that the only realistic data source was the DITL data sets, Day in the Life of the Internet, which are maintained by DNS.org, a membership organization. So every year, a number of organizations contribute their DNS traffic to DNS.org. So they send everything, all the traffic they get and all the responses they get back, and the DNS.org organization maintains that data. But you can only get access to that data if you're a member of DNS.org. So guess what? My firm became a member of DNS.org. We then had discussions with some of the guys from NetNode who are actually here at this meeting as well. And we were given access to one of the analysis machines that they had on offer, EN1. This was a very, very old, very, very, very slow machine. And we did some prototyping on that with a tool called PacketQueue, which the NetNode people were using themselves. It was also developed with IIS, the Swedish Domain Name Registry. So we got some horrible shocks from that. The first thing was that looking at some random samples of the PCAP files that were in the DITL data sets, we found that roughly about 1,000 of those new top-level domains appeared somewhere inside those PCAP files from the DITL exercises, Day in the Life of the Internet exercise. That was troubling. My personal gut feel was we might have found 4 or 5, but not 1,000 of them. The bigger concern was that it took over a week to 2 weeks to process a year's DITL data sets on that box. We didn't have that length of time because we need to make at least 2 passes over the data, and ideally we're going to make passes over the data for 2 years of DITL data. So this was going to be the DITL data for 2012 and then for 2013, because the DITL data exercise for 2013 was just about to get underway. So luckily, Kida, a research organisation, came to the rescue. They had a machine that was available, and we could use that to actually do the analysis and the number crunching on the stuff. We also had some other crazy ideas around, could we actually NFS mount the OARC data sets somewhere and throw a whole load of processors in the cloud at it, get access to a whole bunch of machines from Google or Amazon or whoever, and maybe we could solve the problem that way. But that wasn't an option for a variety of reasons. So we got hold of this 8-core box that Kida had. It was running a very old version of FreeBSD, and we could run through that, and a year's data set would take roughly a week, and that was just about doable. So we had essentially 4 weeks to do all the computation to gather the data, and that would just about leave enough time to write up the report and meet ICANN's deadline to have a report ready for that 6 weeks. So we got hold of this tool called PacketQueue. PacketQueue is a wonderful tool for analysing DNS traffic. So it takes PCAP files or compressed PCAP files. You have a command-like language which is kind of like SQL, and it's very, very good for counting things. So you can count it and find things like where's the most commonly used source address for these queries, what's the most popular query name, what's the breakdown of query types, all that kind of stuff. Very, very good at that. It wasn't so good for label positioning count, so we ended up doing for the second pass of the data, using a combination of TCP dump, ENOG and grep to do that kind of stuff. And this was then the mechanism we used to gather the second level of data, was finding out how often these important names, the GTLD names, how often they appeared at the second or third label position inside the query traffic that's going to the root servers. So what we're looking at there from a scaling point of view, well, typically 1 year's root server data traffic consists of around about 7 terabytes worth of data, and of the order of 250,000 PCAP files. Sometimes it's more, sometimes it's less. It depends on how many root server operators contribute to that year's DITL data sets. So the very first year that DITL was done back in 2006, I think only 1 or 2 root server operators took part, but later on we actually end up getting pretty much most of them. And in actual fact, for the 2017 exercise, which completed just about a month or 2 ago, there were 5 terabytes worth of data and around 500,000 cleaned up PCAP files. What also made this awkward was each of those root server operators had their own file naming convention for these files. So there was usually some combination of the date. Sometimes it would be each file would be broken down by root server by hour. Sometimes it would be everything for a 24-hour period. And they would also use conventions that involved typically the ACAO code of the nearest airport. This is particularly true for the root server operators using anycasting. So if they were using, let's say, for example, an Anycast node that was based in St. Petersburg, that would be a file name that might contain the word LED in it, because LED is the code for the local airport here. So what I did roughly was to take each of those 250,000 files, roughly speaking, chop them up into 8 equal pieces, because I had 8 processors to play with, and run a script over those things, file by file by file. So the idea was to take the process of each file individually. So if something went wrong or the process failed in some way, you just went on to the next one. So you ran through everything, you didn't go back, didn't stop, keep going forward. If there were any problems in any of the files later on, you could maybe come back and have a look at them later by hand. So the idea was always keep on crunching, never stop, never go back. So what we're doing then was essentially a process of 3-stage distillation. We had of the orders of terabytes worth of data. We would then distill that down into the order of gigabytes worth of rough results, and then distill that further down into megabytes worth of results, and then I could pass those megabytes of results on to another member of the project team who could then throw them into a spreadsheet and then generate graphs and PHP tools and all the rest of it, which could then go into the final report that was produced. I didn't do that work, I just produced the results. So some of you might be asking yourselves, well, why didn't Jim use Perl? Why didn't he use Python? Why didn't he use this latest tool, that latest tool? Well, there were several reasons for that. The first thing was, this was all on a machine which I didn't have ownership of and I didn't control. So I couldn't really realistically go around installing things like the latest version of Perl or Python. And frankly, I didn't have the time for that either. There was no time. If I had to install Perl on this machine, then I might have to get some other package, and that would depend on this, and then installing this new compiler or whatever. There was no time to get involved in that. I just had to use essentially what was there and make the best of what I had available. So the result of that was I couldn't, to use a Scottish word, I couldn't bluter anything on the existing machine. Bluter is a Scottish word which means to hit something with great force and very little skill. For example, the footballer blutered the ball over the bar, missed an open goal. Anyway, the only thing we did have to do though was install the latest version of G++, because PacketQueue is written in C++ and it needs the latest features that are found in the latest versions of G++. Next question is, why didn't we use a database? Well, first of all, again, we had no time. We had 6 weeks essentially to get this project finished. There were just far too many unknowns to even think about using a database. How big would it be? Don't know. What would be the right size to choose for the tables and indexes? Don't know. How long would it take to populate that database? We don't know. How long would it take to run SQL queries over that database? Your guess is as good as mine. We couldn't prototype that even if we wanted to. So the simple answer was, forget that. Forget Hadoop. Forget any of that new stuff at all. We just have to use raw brute force to get things done. So when we started to get the findings out of that, there were lots and lots and lots of power law distributions found throughout these data sets in all sorts of areas. Every time you looked at some aspect of the results, we would find some kind of power law distribution. We would find that you would find that there were 2 or 3 TLDs that accounted for most of the traffic, and then there'd be a long, long tail of everything afterwards. There was far more traffic for all the new top-level domains than anybody originally thought. Pretty much all of them were found in one way or another. And the traffic for the proposed domain names .home and .corp was particularly high. In actual fact, .home, even today, is one of the most frequently queried top-level domains that gets to the root server traffic. It's bigger than just about everything else other than ARPA, COM, and .net. There were other things that we thought should have been looked at. There were queries for things to do with MX records and SRV records. And we thought, this is something that's been deliberately configured to go and look for these things. This is not accidental stuff. So this can't be coming from a naive user or an accidental use by an application. Something was deliberately looking for that. And we thought that was more significant than just going with the raw numbers of this particular TLD had so many queries and so on. But I can't disagree with that. Also at that time, I was working for the Norwegian registry .no, and they have 2 other top-level domains that they're responsible for, 2 country codes, .bv, Bouvet Island, and Svalbard Island. One's up north of the Arctic Circle, and one's down in the very south near Antarctica. Both of those top-level domains are completely empty and unused. Well, they were at the time. BV's now been sold off, and lots of Dutch companies are registering their domain names there. But at that time, both of those domain names were completely empty. They contained nothing other than the DNS metadata, the SOA record and the NS records and glue. There was nothing else in them. So we could use that almost as a sort of baseline level. You could argue that as being, that would be like the background radiation of the DNS system. And each of those top-level domains was getting of the order of about 50,000 queries a day. So we think most of that traffic is coming from monitoring systems, checking to see if the top-level domains are up there and active and responding. But that was kind of what we thought, and ICANN decided that if a top-level domain was below that threshold, it was considered safe. Anything above that was having to go through some kind of risk mitigation measures. So here are some numbers just to show you what's there, and what I've got here are by percentages rather than absolute numbers, because the absolute numbers changed year after year because the data sets got bigger as more and more root server operators contributed data to the DITL exercises. So trying to compare this numerically in absolute terms would be probably a bad thing to do in this kind of setting. So as I hope you can see there that roughly 22% of the data traffic in 2006 was coming for .com, then it was net ARPA. The category there which I've got as others are for strings which were not known. In this case, we're talking about strings which are not top-level domains that already exist or top-level domains that ICANN was planning to create. So this ended up being things like localhost, local domain, Belkin, HTML. These were the things that actually appeared in the others category. And as you can see, almost 10% of the others were for these kind of names. So still similar kind of distribution year after year. I think we'll find the moment Russia eventually puts in appearance. There we are. Russian appears the first time in 2009. So it was the fifth most popularly queried top-level domain on the internet in the DITL exercise for 2009. But it's still only accounted for something like 1 or 2% of the overall query traffic. Russia's still there, still sitting there at the same kind of level. And you see these numbers continue pretty much following the same pattern. But we see later on in the years that the others traffic starts to creep up. And again, this other category, I've taken another look at this data set to see what's going on there, and it's not coming from a specific string. It's a random set of strings coming from all over the place. Things like Belkin.home, localhost, local domain account for the vast majority of the stuff in this others category. And here we see the same thing going on. So ICANN's initial approach at this stage was to say that the .home and the .corp top-level domains were essentially dead. There's too much traffic for them. There's no chance of these top-level domains ever being created. Well, to all intents and purposes, that's what's going to happen to them. ICANN then also decided that delegating .mail, which is another of the top-level domains that had been requested, that too would also be rejected because, again, it was too risky. The other ones, ICANN decided, could proceed to delegation, but they would need to do some kind of risk mitigation strategy. So the idea that they would create the top-level domain, but before they went live, they would have wildcard records that pointed to a non-existent IP address, 127.053.53, and there would be a text message that says, your DNS is broken, you shouldn't have come here, please go and talk to ICANN and tell us about how you got to this, but you found this information. And there were a few cases where people did actually contact ICANN to say, we saw these messages, could you please explain what was going on? So before they got there, ICANN had another idea, which was to actually synthesize the NX domain responses that you get back from the DNS. Excuse me for a moment. So the plan would be is that at the moment, the root servers would return an NX domain response if someone did a query for, let's say, .mail as a top-level domain. The root servers would return NX domain. ICANN's initial plan would be is though, what we'll do is we'll actually delegate .mail and have the new .mail DNS servers return the NX domain, not the root servers. Now, was that strategy a wise one or not? So this was the second thing that I did as another exercise, which was not something that ICANN asked to be done. This is something I did myself for my own entertainment value. So here we have a conventional DNS lookup. You've got an end client, makes a query to its local resolving server, sends a query to one of the root servers. The root server says, new TLD doesn't exist, get lost. The resolving server returns that message back to the end client and everybody's happy. And after if new TLD was delegated, we still get the same thing happening, but except this time, the root server returns a referral response which says, here's the names and addresses of the servers for whatever it is. Go and ask them. The resolving server then makes the query to one of those servers, and it returns the NX domain response, which is then returned back to the end client. So far, so good. We've seen that all before. Now, what happens if there's an undelegated to be, or what I call a naive client? So let's say a stub resolver that queries the root server directly, or some kind of forwarding thing, say for example in some middle box, or in let's say a DSL modem or something like that. What would happen in that case? Well, in the conventional model, it would make a query to the root server would return a response that says, NX domain, it doesn't exist, go away. What happens now? Well, it would then return a referral response instead of this NX domain response, and of course the end client doesn't know how to deal with that. Bad things would happen. Maybe the client will crash, maybe it will fail, it will certainly behave in strange ways. What would it do? Nobody really knew. So these would typically come for things like stub resolvers, forwarding only servers and stuff like that. What would they do if they got a referral response instead of this NX domain that was being proposed? So the idea was to find out is how much of a problem could that be, and also what top-level domains were more at risk from it. So by this time now, we're now crunching 10 terabytes worth of DITL data. So we're looking at roughly 250 billion queries in the PCAP files. So this was running through all the PCAP files from 2006, 2013. So we made 3 passes over that data, doing all sorts of analysis, qualitative, quantitative, historical, and comparative. So the first shocking finding from that is that there's quite a lot of traffic that sets the recursion desired bit. Roughly 12% of the queries that go to the root server system today, roughly 12% of them are coming from devices that set the RD bit. So they're coming from devices that want the root servers to do recursion for them. This is something that shouldn't be happening. The only things that really should be querying the root servers are resolving servers, and of course they do the recursion themselves. Pretty much nothing is doing recursion available, setting the RE bit, and that's a good thing because only servers that answer are supposed to set the RE bit in the DNS headers. So that was kind of a reassuring result, even though the RD thing did create some concern. So where are these traffic coming from? Well, most of it, surprise, surprise, is coming, broadly speaking, for the most popular top-level domains already used on the internet, .com, .net, .arpa, .org, and so on. Very few of the new top-level domains where query traffic had this RD1 bit set, so the recursion desired bit was only appearing for a very few of these top-level domains. And again, by far the biggest source of those were queries for .home and .corp. Or for the others, most of them had none at all. And there are also quite a few for .google as well. So we were looking at also from a historical perspective to see is, did this pattern of behaviour change between 2006 and 2013? And if so, how did it change? So broadly speaking, things were stable year after year after year. The traffic levels were roughly about the same, the percentages were roughly about the same. There were 1 or 2 spikes, but most of it was fairly consistent. So overall, things were behaving pretty much all the way. There wasn't much sign of any new stuff changing things or perturbing the data. So here we have a look here at a little graph that shows of the total number of requests. We see a spike in 2010. We had roughly 40 billion queries in that year that had set the RD1 bit, had been set. So if we then take that for the current top-level domains, we can see there the counts there were roughly about 8 billion of those queries were set, and that 8 billion queries were pretty much all for .com. The rest of them you can see are pretty much flat. They're certainly less than a billion or just slightly more than a billion, not as significant. So then looking at that, what about the new top-level domains that are being proposed? What are the rates for them? Well, on the next graph, now we're looking, if you now look at the y-axis for that graph, we've got the counts in millions, not billions. So we've dropped by 3 orders of magnitude to have to deal with the rates for the rates other than .com. So if we know .com, we take these things to try and see if we can get some more fine detail in the graphs. We still see it's relatively slow, it's still relatively stable, and we're talking of the order, mostly of the order of around about 400 to 500 million queries that set the RD bit. And again, taking this for the new top-level domains, we come down yet more orders of magnitude. So instead of going from billions to then millions, we're now in the thousands. And you can see there the numbers are insignificant. So we're talking, broadly speaking, we've gone from 70 billion queries to looking at 70,000 queries. So really, there's really not a big deal. There's really not a great cause for concern there. So I then decided to look at this from the point of view as well, that safe threshold that I can set of 50,000 queries, if a top-level domain was beneath that, there was no need to look at those. So let's look at some of these things in a little bit more detail and see what we found. Well, in 2013, roughly 57,000 of the queries that set RD1, that had the RD bit set, came from a school in California that was looking for .google. One IP address set all the queries for .state farm, a US insurance company. Pretty much all the rest came from RFC 1918 addresses. They shouldn't have been reading the root server at all because it's private IP addresses. So we couldn't identify the root sources of that traffic. In 2012, the Google data traffic was a bit more diffuse. It was coming from roughly about 600/24s, each of which generated of the order of 500, 600 queries. Personally not worth worrying about, I think. And again, there were quite a few of these 1918 addresses in there too. And a lot of those queries we saw there were actually looked like valid Google queries. Gmail-smtpin.l.google. Someone's obviously forgot to append the suffix .com or .ru or .whatever. So it's probably a transient error in someone's stub resolver or a mail server configuration that caused it that year. Another one that was very entertaining was the queries for .anz, the Australian New Zealand National Bank. This was quite amusing because Australian National Bank said, all the queries for .anz are coming from us and from nobody else. We know this. No, that's not true. There's where the queries are coming from, and they've got these gloriously bizarre, very, very long query names with 10, 15 labels in them, ending in .anz. Now, I don't recognise that language at all. If anybody can identify it, I think it might be Farsi, written in English, but I really do not know what that is. But it's clearly got nothing whatsoever to do with the Australian New Zealand National Bank. We also saw quite a few queries for .mail, but again, we're talking of the order again of a few hundred /24s, and each of them were generating roughly 300 to 500 requests. Probably not worth trying to investigate further. You know, could you go and ask someone 6 years ago, can you explain why you were generating queries for .mail that set the RD1 bit? Good luck if you could find a system administrator that could actually explain that away to you. Another one which I really liked was in 2008. There were a lot of queries for Klingon.site, 60,000 of them. And they all had the same query ID, and they all had the same port number. And they all came from a single IP address belonging to the University of Toronto. No reverse DNS entry for that IP address. So I've got two potential theories about that. Either it was a student programming exercise that went wrong, or else Mr. Spock doesn't know how to write DNS code. He can't program properly. One of those two theories is probably true, but I don't know which one of those. Maybe it's not Mr. Spock, maybe it's Captain Kirk. I don't know. So, what were the overall findings for this exercise? We found there was an awful lot of RD1 traffic, recursion desired traffic going to the root, and that's pretty much static year after year. And it's round about 12%, sometimes a bit more than that. One year it's maybe a little bit less, but broadly speaking, around 12% of the traffic that goes, DNS traffic that goes to the root servers sets the RD1 bit, recursion desired. So it's not coming, or it's probably not coming from resolving servers, it's coming from stub resolvers and forwarding setups, stupid proxies and things of that nature. And that very high traffic level doesn't appear to be breaking anything just now. So these naive clients that are making these queries that are getting referral responses back from the root server, they're not failing in ways which are causing bad things to happen. Nobody's saying the sky's falling in, nobody's finding applications failing, but this background is going on time after time after time, and it doesn't seem to be causing any great problem. And for the repairers, they are getting back for referrals for .com and for .net and for .arpa. That doesn't seem to be creating any problem. So if a naive client is getting a referral response back, they're looking up example.com and they get a referral to the com servers, they can somehow cope with that. They're not crashing and burning and causing people to scream and shout and do all sorts of nasty things. So the actual traffic levels that were in place for the proposed new top-level domains was much, much, much lower, both in absolute and relative terms, than the rates that are found for the existing top-level domains. So instead of having RD1 queries of the order of billions for .com and .net and so on, we're talking in the tens of thousands for some of the more commonly used or potentially commonly used traffic that's going for, let's say, .google or whatever. The traffic for Google kind of concerned me a little bit because that's obviously a fairly popular domain name and lots of stuff uses that. But it didn't appear to be isolated incidents rather than sort of general pattern of behaviour. So it looked as if it's something that would be containable and not really such a big deal. We had a fairly low and stable rate for .mail. So this potentially could have been a problem because that might mean that corporate mail or whatever was getting blocked or delayed because of these NX domain responses. But again, if this was creating a problem just now, we would hopefully have known about it or someone would have detected it because mail was being sent to the wrong place. But again, or not being sent at all because the lookups were failing. But again, didn't seem to be causing any problems, so who cares? So the upshot of that was that that initial proposed strategy that ICANN had for blocking the names wasn't really going to create any problems. They actually chose something else in the final analysis, which they used as wildcard technique, but the initial approach, which again was done before having gathered some data beforehand, that approach would probably have been okay too. So finally, I need to say thank you to a lot of people. Although all of this work was essentially mine, I couldn't have done that without the help from Casey Claffey and Daniel Anderson at Kida. Dan was the system administrator. Casey was responsible for the machine. She kindly donated it to me for the purposes of this exercise. And after I had hammered that box into the ground for a month, it died. So it died a noble death. And Dan was the system administrator that installed the latest version of G++ for me. I also have to thank Heinrich Lefkowitz from NetNode because Heinrich was one of the main authors of the PacketQueue software. So he provided some assistance both in terms of technical support for the software and double checking some of my initial results against the data sets that NetNode had for their PCAP files because NetNode run one of the root servers and they also contributed data to Kida. We found an interesting little bug because one of the raw PCAP files, one of the root server operators was using VLAN encapsulation and PacketQueue didn't know how to handle those particular PCAP files. So it couldn't actually see the actual frames inside the frames where the IP packet started and then the DNS packet started inside the UDP headers inside the IP packets. So the result of that was you would run through a whole PCAP file and get no output at the end of it because everything was offset by 2 bytes or 2 octets. So Henrik very, very quickly fixed that for me. And also I need to thank the guys at work. We couldn't have done that with access to their data sets and to William, who was the system administrator, who was giving some advice about how to try and tune things and get some of the NFS things done. Because what we actually did was the analysis servers NFS mount the file servers that contained all these data sets. So we're putting this across gigabit Ethernet and then had to tune the NFS settings on this so it could cope with processing huge amounts of data in that pace of time. And finally, before we get to questions, I would also like to say thank you very much to the very nice people in the booth at the back of the room that are doing the simultaneous translation. You're doing a great job and I'm impressed mightily with all you're doing here. I think it's an incredibly hard thing to do and I think we all owe you a great deal of thanks for that as well. With that, I'm happy to take questions in Russian or English.
And I actually thought we should have done this talk together because I've got some additional information about this thing. I did some work for ICANN for looking at the influence of the delegated new GTUDs on the whole system. And the report is a couple of months old and it has a lot of interesting data, kind of matches your data. But just for fun, I mean, you should realize that the traffic, the last time I looked, for .home, corp and mail is about 5% of all the traffic, and it's about 10 to 20 times more than all the new GTUDs together. So that gives you an idea about how these things work. And the other thing is, PacketQueue, we didn't use that because it was way too slow. We actually generated small little programs exactly asking the questions we did. And since the hardware was replaced by a bigger box with lots more cores. I could actually run stuff in parallel,
Yeah.
so I could wait. Because the bottleneck was there, the NFS, so that made life slightly more easy than it was. The other thing is, PacketQueue is actually officially now available for the rest of the world since yesterday.
Yeah.
And so it's a new version, and I've made it run on BSD.
Okay,
and,
well, let me take responses to all of those three things you just said in reverse order. PacketQueue was kind of abandoned for a while because NetNode and IS decided they weren't going to continue to maintain the software, but it has just been handed over to DNS at Work. So DNS at Work now has the software, it's in the public domain, and DNS at Work is going to maintain the software and hopefully continue to develop it. I think PacketQueue is a wonderful, wonderful tool, and if you've got the chance to use it for analysing PCAP files with DNS data, accept those substitutes, it's a wonderful, wonderful thing. Second thing was on the computing resources. One of the lovely beneficial side effects of this work was that DNS at Work was given donations of new hardware. So ICANN gave them some new big fancy powerful machines, 64 core processor, things like that, 16 core processors. One of the GTLD operators, new GTLD operators, also donated a machine. So nowadays you can now run through a digital data set of about 5 terabytes in, roughly speaking, 8 hours, or maybe even less than that. When I was doing it, it was taking 1 week, driving 8 cores simultaneously. On the new machines, we can get it down to driving all the cores simultaneously and down to roughly about 8 hours, or maybe even less than that in certain cases. And also your first point, .home. This TLD is generating roughly about 3 to 4% of the traffic to the route today. And one of the most surprising things about that is that after the announcement that .home was going to be frozen or essentially killed because of the fact it was generating too much traffic, the traffic levels for .home went up. You would have thought that if someone was wanting to get the .home delegation done, they wanted to try to get the traffic levels down, and the sponsors of that top level domain would do what they could to stop things like DSL modems or whatever it is, trying to find out what was generating its traffic and put a stop to it. But the reality is different. The traffic levels are increasing, so .home generates more traffic than just about every other top level domain on the internet, more than we get for the root, more than we get for RU, DE, CN, UK. So the only domain names, top level domains that get more traffic than .home typically are COM, NET, and ARPA. Sorry, Jaap.
Yeah, well, there's another question. I mean, what I had. There's one of the things that we think that will actually start to kick in is doing query name minimization. So you don't see less data coming up to the root. It's this will be interesting for future comparison. And the stuff you see at the root is actually amazing. I mean,
Yes.
half net, you see complete web pages being used.
There's all sorts of crap in the root server data set.
It's amazing. The .Google problem, I mean, people in Google tell me they're actually actively working on getting rid of some of these queries. What was actually a real question, I noticed that the data was not really consistent. There are some root servers which have big holes in the data and things like that. And I didn't look at the new batch yet, but how did you cope with that?
Well, you didn't. I just had to take the digital data sets as they were. We realised they're incomplete. We realised that you've not got all the traffic, and of course we're just taking a snapshot of what the DNS traffic was for one given day. So there's no guarantee that that pattern of behaviour for that given day is the same as the other 365 days of the year.
Right.
So we don't know that either. And also, some of the root server operators were only giving partial data sets. They didn't have everything. And also, not all of the root server operators contributed data to the exercise every year. Pretty much, I think there's only one that doesn't contribute data now. I think it's just the G root server doesn't contribute data. But I think the plan is for next year, they will be doing that. One other interesting thing which I should have mentioned in my talk was I would really like to meet someone from Google and have a big baseball bat with me, because we found one of the interesting things that was in the data sets in later years was we saw lots and lots of 10 single query labels for 10 character strings, which were unique.
Google.
They were used exactly once, and this was the Chrome browser. So the browser was generating these unique 10 character strings, trying to see if they're getting an NX domain response or not, because then it was trying to work around ISPs that were trying to do NX domain rewriting to point you at some kind of landing page or sell your domain name or whatever. But I had to count every single one of those 200, 300 million 10 character strings, because I didn't know at the start of the exercise if that string was going to appear more than once in a given year's data set. I didn't know that up front, so I had to count these things. That was very, very annoying. It made my job a lot harder than it needed to be.
Yeah, a lot of people had a problem with that, with doing other stuff. But let's talk about the rest over beer. Time for lunch.
Коллеги, последний вопрос, если есть короткий.
The last question, dear colleagues, please, if you have some